We are here talking about the quotient rule of differentiation. So you've done the product rule, and it's actually linked to the product rule. It's a quotient rule, so it's a division of two different functions. So if I have f of x is equal to u of x over v of x, as in some expression in x, and then you divide it by v of x. So for instance, you could have something like this, like e.g. you could have anything, x squared over x cubed minus 1. Right, that's an example of something over something. And so in this case, we do that. Now, this bit that I've just started here, this arrow, the variation of the product rule, this is kind of a proof of how we get using the product rule to the quotient rule. Now, I'm going to say to you that look through it and ask me questions if you want. But really, the thing that we need to focus on is the result. So it's here. When you have u over v, it's this final result, that f dash x is equal to vu dash, so the function in the denominator, multiply the derivative of the numerator minus the numerator function times the derivative of the denominator, and that's all over the square of the denominator function. All right, so that's the thing we want to know. Now, it is in our reference sheet, but it's good to sort of be aware of it. So let's have a look and do some examples. Now, the difficulty is not in the differentiation. You should be able to do that of each part. The difficulty is going to be in the making sure that you use algebra correctly and taking it step by step. So let's hope that we can find our way to do that. Okay, so first one. 3x minus 1 over x plus 6. All right, now is this a case for the quotient function? Well, yes, it is, because it's u, something, a function in terms of x, over another function in terms of x. So what I would suggest for you is that you actually write what's what out next to it. So in this case, u is equal to 3x minus 1, and u dash, as in the derivative of u, well, the derivative of 3x minus 1 is just 3. The denominator function is my v, and that's just x plus 6. Now, v dash is equal to, well, the derivative of x plus 6 is just 1. So, y dash, let's use the proper notation. Well, it's not proper, but let's use the full notation. dy dx is equal to, so it's vu dash, so it's x plus 6 times 3 minus uv dash, 3x minus 1 times 1 over v squared, so x plus 6 all squared. As much as possible, the first step, you want to be just substituting directly in. Not trying to do too much manipulation at once, otherwise you've got to make errors as you go along. Now we start to expand. Okay, so it's 3 times x, so it's 3x. 3 times 6 is 18. Now, because it's multiplied by 1 here, that just goes away. We don't need to write that. So it's minus 3x minus minus 1, which is plus 1. So it's minus 3x plus 1. Now, that's an interesting case. Oh, I forgot to write the x. And then I'm not going to expand the bottom. I just want to leave it in factored form. Now, if I simplify the numerator, 3x minus 3x is 0. 18 plus 1 is 19 over x plus 6 all squared. So that is the derivative, that's the gradient function, dy dx. It's the gradient function of my 3x minus 1 over x plus 6. So at any point I could find out what's the rate of change of this function, 3x minus 1 over x plus 6. So if I wanted to say, okay, e.g. find the gradient, so I'll just do this as an aside, find gradient of y when x is equal to 1, well, you just sub in. So you sub x equals 1 into dy dx. That gives me the gradient. So it's 19 over 1 plus 6 all squared. Now, it's not a particularly nice number. Going to be 19 over 49, which is approximately 0.4 2/5. But it gives you an idea that what are we doing? We're finding the gradient function which gives me the instantaneous rate of change of the curve, right? And if I want to know the gradient at a particular point, I simply take that point and I sub it into the gradient function. Okay, so that's number one. Now, number two, which I probably should put number two, I've got here. Now, very similar. We've got u over v. So my u is equal to x, right? And remember, u and v are functions that have x in them, functions of x, right? So u dash, which I could think of as du dx, so I'm differentiating u with respect to x. What's the derivative of x? Well, it's just 1. V is equal to 1 plus x squared. So v dash, which is another way of saying dv dx, I'm just differentiating or finding the derivative of v. What is that? Well, the derivative of 1 plus 2x and 1 plus x squared is just 2x. The 1 is a constant, so it just goes away to 0, and we have that. Now, I'm just going to insert a bit of space here. So, if we do f dash x, what do we get? Well, again, it's vu dash 1 plus x squared times 1 minus uv dash, right? So it's going to be minus x times v dash, which is 2x, over v squared. So that's 1 plus x squared squared. Okay, now once I've substituted things in correctly, I would then expand and simplify. So it's 1 plus x squared, because I'm just multiplying by 1, it doesn't change, minus 2x squared over 1 plus x squared all squared. And this becomes 1 minus x squared over 1 plus x squared. 1 plus x squared all squared. Now, that can't simplify. You can't just start randomly cutting out x's and say, oh, there's x squared on the top, x squared on the bottom, there must be common. No, it has to be a common factor. So don't go randomly chopping and changing things out. Make sure you can factorize first and then find common factors. So again, I'll emphasize f dash x, or sometimes called f prime x, is simply the derivative, which is the gradient function. So if I want to find the gradient of the curve, x over 1 plus x squared at some point, I would substitute that point into my derivative, which is 1 minus x squared over 1 plus x squared all squared. When you're using the quotient rule, you can very often get very complicated things. Now, the next example, you need to look at very carefully, take step by step. If you're not sure of anything, make sure you check. So here we go.